So shall we begin?
Yeah, I just started the recording. Go ahead.
Awesome. So let me see if I can make it sound right. So Yorgos Hinzoglou, he is a senior scientist at Lockheed Martin, where he joined it in 2021. But before that, he actually worked at UCAR as a project scientist, and he worked with AIA and IRIS. Before that, he was a postdoc at UCAR via the Visiting Science program. He got his PhD in George Mason University, and he got his bachelor's in physics from the University of Ioannina in Greece, of which he is a native. And his primary research areas are in the physics of the solar magnetism, solar active region evolution, and associated activity, as well as the CME initiation theory, as well as the interpretation of observations. So Yorgos has a strong research in instrumentation, and he is an instrument scientist right now working on the calibration of the IRIS mission. He is also actively involved with the design and development of the slit geo imager for the upcoming UVST, which is a joint mission of NASA and JAXA. And he's also involved with the design, testing, and development of the MUSE, which had been recently selected. And with that, please, you have the scene.
Thanks, Annie. Thanks for the invitation as well. Thanks, everyone. Let's get to it. So active regions basically are concentrations of magnetic fields on the solar surface as we see them, and perforating magnetic fields that are perforating the surface and extend all the way to the outer atmosphere. And they have a characteristic time scale of evolution. Here you see an active region tracked from limb to limb, almost 14 days of transit time, and you also see the associated activity in this X-ray flux plot from the GOES satellite. On the right, we show also an illustration from a recent publication, maybe not so recent anymore, where we discussed the canonical evolution of magnetic field emergence and as a lifetime of essentially a simple dipole. So initially you have the emergence of magnetic fields, and then shortly after the end of emergence, there is the decay phase of the magnetic fields, where the magnetic polarities are losing the cohesion and become more extended, and at the end they begin to interact with each other. We call this flux cancellation. And that's for active region scale magnetic concentrations on the sun. When we go to smaller scales, we see something completely different. We see that we have, some people like to call it a magnetic carpet, but we have a multitude of small dipoles emerging all over the place, anywhere you look at the sun. Here we have some very nice, the NFI observations. NFI is not available anymore, but it took very, very important observations of small-scale magnetic features, with making very deep exposures. And that's one of the longest data sets that were achieved with using continuous pointing, where you see the continuous evolution of almost 2 days on the sun. So in the center, you see, I think in the beginning of the movie, if I play it back again, you see a nice supergranule. You can see it by the way the magnetic fields are coalescing in the so-called internetwork region. And in the center of the supergranule, you see emergence of multiple dipoles, and as you see, they are being they appear to translate towards the edges of the supergranule. And as they move, they either coalesce and they form larger concentrations, for example here, or if they have opposite polarities, they collide and they annihilate. So maybe I can just guide your attention, but anywhere you look in this movie, you will actually see these effects, such as say emergence and cancellation. Cancellation has been discovered in the mid-80s by Sarah Martin, by the way. And we'll discuss in this talk the possibility of magnetic cancellation during emergence in large-scale structures like active regions, just to summarize that. And of course, the associated activity. So after this short overview, we are ready, I think, to start discussing about how we can characterize solar activity, first of all. And one way to do it, sorry for this busy slide, but we typically use nowadays the X-ray flux measurements from the GOES satellite. This has been going on since the early 70s with the first GO satellite. Has been this X-ray flux monitor program, and allows us nowadays to have almost 5 decades of continuous surveillance of the X-ray output of the sun from space. So the way we typically talk about events is we look at the GOES flare classification, where for the old timers, I don't know if there are any in the audience, we used to look at the so-called flare importance, which was really a scheme that was classifying how strong the flares we're seeing in H alpha. But now we're using this letter and a numerical code. The letter is X for X flares, that is the strongest flares, M for flares that are actually 10 times weaker, C for the flares that are 100 times weaker than an X flare, and B and A, correspondingly to lower orders of magnitude. So the way to characterize the total output of flare activity on the sun, we can use a so-called total flare index, as was defined by Antalova, 1996, I believe. And here you see just converting the letter of the flare classification, the class, into a statistical weight, and just summing the magnitudes as numbers and producing a singular number. So in essence, with this kind of description, by attributing a statistical weight of 1 for C flares, we are converting all flare outputs from a particular active region into units of a C1 flare. So when you have 1 X flare, this corresponds to 100 C flares, C1 flares. 1x1 flare, sorry. And another thing that I want to point out in this slide is that not all active regions really are producing major flares. Major is typically defined as the M flares and above. But I would argue here that the total flare index is actually a more accurate way of describing the total flaring output of an active region, because you may have multiple C flares, and overall they may coalesce into something that is as important as an X flare, for example, or more. We also have a problem, though, when we want to study active regions. The thing is that the sun is rotating. We're not co-rotating with our star, which is probably a good thing. And here is what happens. When active regions really appear, that's great. We actually managed to capture, well, they essentially emerge. We managed to capture the birth, the time of their birth. Therefore, we can start tracking their evolution. We go from early stages, like a baby active region, all the way to adolescence and middle age, and then all the way to its decay. But that's not what happens at all times. Active regions really pop up at random longitudes, even though they are they appear in not so random latitudes, so to speak. We have the Sporer's law that defines where they are. So they rarely exceed 40 degrees north, if not 35 as a better number. North-south, sorry. Heliographic position in latitudes. So the problem is that when active regions emerge on the west hemisphere, we do not have a lot of time, because the sun rotates from east to west, right, as we see it, the apparent rotation. And therefore, we cannot really do much with them. And in this description here, and what you will see in the following slides, we reject such cases, any strong active regions or any active regions that really emerged in that particular area, because we only have a few days to study them. And active regions evolve in multiple days, not just in a couple of days. At least the very flare productive ones. Same goes for active regions that emerged, that appeared already developed in the east limb as the solar rotation brings them into view, which means that they have probably emerged in the side of the sun that we do not observe from our vantage point. So we also like to disregard such cases, because we cannot really do this kind of robust study of the active region evolution from the birth to the decay, because we are missing their birth. So we will propose here to only focus on newly emerging active regions that emerge in the east hemisphere of the sun. And that's what you will see. Let's look at a few cases here. So here you're going to see a case which produced over a period of 8 days, a total flare index of 8. So as you see, on the left is a magnetogram series. Here you see a small figure that shows where it was emerging. It's in the North Hemisphere. And on the right, you see the intensity maps, which show the sunspots essentially and the granulation all over. You don't really see the granulation, I'm sure, right now. But anyway, you can imagine it. And what you see essentially is a canonical bipole. This is really a very simple case. And it's not really something that is surprising that active regions that are very, very simple in structure, we call those beta type active regions in the so-called HAO or Mount Wilson classification for the complexity. Sorry, I'm looping this manually. We don't really have a lot of activity emanating from them. So you just see 2 sunspots here, and that's it. Now let's look at a more complicated case. That's a case that emerged the South Hemisphere in that particular location. And I think most of you in the audience have probably studied this active region. So you see this active region is basically the result of 2 bipoles emerging side by side. And if I play it again, you see there are colliding. The negative polarity of one dipole collides with another one. And of course, there is secondary and tertiary emergence as the time goes on. But overall, the initial stages of the evolution are very well described by 2 bipoles emerging side by side with different orientations, which are positioned in a way that collision really happens and producing a delta spot, essentially. Delta spot is when you have 2 sunspots sharing the same penumbra, essentially, as a morphological feature, meaning the same. And at the same time, you have different polarities within the same penumbra, and that's really what you see. And the surprising thing here, maybe, is that the total flare index for this active region was almost 600. So an equivalent of what? 600 C1 flares or 6 X1 flares, just to give you another way of thinking about it. One more time. Very consistent with what we know about complexity of active regions and evolution. Now, here is how active regions rank. If we really focus on active regions that I said emerge, we see the first stage of emergence in the East Hemisphere within this kind of region, up to 70 degrees, I believe, or something like that, that I have here in this plot. And strictly stopping considering cases at the central meridian. So we reject any other case, as I said. This is how they rank. So I have the top 25 active regions with respect to total flare index. So on the top left, you have the most flare productive active region that we managed to capture its birth and track it for a significant amount of time, at least 8 to 10 days. And you go row by row to lower flare index. So you can, if you can actually read the numbers, maybe you can't, but I can read it for you. The top left one is 616. Total flare index, and the second one is the active region that I showed you before, the movie with the 2 bipoles, the active region 1158. So very similar, and as you see, that has been a very well-studied active region for multiple reasons. It was extremely flare productive and very well observed in those kind of terms. And you may also notice that the flare index, which is actually the second number that you see here after the forward slash, and if you don't see it, I will just tell you that the total flare index in the bottom right is actually only 50. So that's how rapidly the flare index drops. However, the main takeaway message from this presentation of different cases, the top 25 cases we observed really well in the previous solar cycle, were multipolar. Basically, were composed out of multiple bipoles, and 2, they were not just multipolar and having polarity sitting there, they were colliding. At least 2 polarities were involved in sunspot collision, and that was correlated with the onset of explosive activity. Now, I said earlier that we'll disregard any cases that appeared completely developed and mature in the east limb, as solar observation brings them into view. But I couldn't resist to actually put these active regions as well here. So any active regions that appeared already developed beyond 70 degrees east, beyond this kind of dotted crescent that you see here. So same thing, same goes here. You have multipolar active regions, and they are they're undergoing collision at some point in their lifetimes. And as we have the privilege to observe these active regions during the entire transient time, at least for 14 days, essentially, depends how you count, if you really consider the activity at the limb and placing it to the total flare index of these active regions, which is probably a fair assumption, but nevertheless, having more accuracy when we observe them on the disk, we observe exactly the same. Multipolar active regions and undergoing collision. So collision is an essential ingredient for what we're going to discuss. And here I put the first set that I showed you and the second set side by side. It may be really difficult to appreciate how multipolar these active regions are because I only saw still frames. But I invite you, if you want to do this exercise, actually I invite you to do this exercise and convince yourselves that this is really the case. Basically, look at movies of multiple active regions, as I've done, and really get to appreciate this fact that we have multiple bipoles emerging at random times and then undergoing collision. That's really the main point of what I want to show. So in summarizing, we're talking about emerging active regions in this case, or still evolving active regions, which means still hosting some emergence here and there, or even motion of polarities. We know that bipolar active regions are actually very weak in terms of flare potential or flare productivity. And there are multiple publications. One that I have here is by Samis et al. 2000. And a very simple study, but passes a very strong message, I think. There have been many speculations about whether the active regions or the bipoles, when they emerge, whether they are twisted flux tubes, and therefore they're already in a form of a highly stressed and free energy containing structure that once it fully emerges, it can blow up and produce eruptions. But when you have such clear bipoles, and you don't see that really, that's what we see in those correlative studies. That may also mean something, that maybe we don't really have a lot of twist in these cases. Of course, we have the magnetic tongues as morphological features when two polarities are separating from each other, but you can explain it in other ways, I guess, like multiple emergence without necessarily a lot of twist. The decay phase of an active region is also something that we didn't really touch upon in the previous plots, but when I say a bipole is not really very flare productive, it doesn't mean that later on in its lifetime will not produce activity. So I'm talking about emerging bipoles. So if it is a simple bipolar active region, you may not really see a lot of activity if it's not really supporting a complex configuration. But later on, when the decay phase enters, you actually have cancellation in the internal neutral line. We also call it self-neutral line of an individual bipole. And it may bring up the conditions to produce structures that eventually erupt. For example, most of those sigmoids that were discussed as structures in Yoko data back in the early 90s were from such active regions. And there is a lot of work done in the literature. You can actually find a lot of publications explaining, in my opinion, very successfully, the physics that lead to such activity at the end of the lifetime of an active region. But nevertheless, the most flare productive active regions are basically emerging active regions, or active regions during their emergence phase. And obviously, when they're more complex, there is even higher potential for such activity, flares and CMEs. In this talk, hopefully I can convince you, or give you my perspective at least of why this is the case and what makes such active regions more special than others. So to summarize what I said earlier about decaying active regions, this is a well-understood process. There are many publications that involving a very well-cited model, which is Van Palekoijen and Martens 1989 model, involving the physics of flux cancellation, which is where you have decaying active regions. You don't really see sunspots anymore. You just see decaying plage. that is dispersing more and more, and then you forming an extended neutral line with cancellation that I showed you earlier, happening in an ordered fashion, essentially, producing eventually a coiled magnetic morphology, magnetic topology. And you can look at Green et al. 2011 for a nice illustration that shows one by one this kind of process as it evolves. And flux cancellation obviously means that you have a reduction in the total flux of the active region. But then what happens to the active regions that are, as I said, extremely flare productive? Why they are so different and more eruptive than the decaying active regions, or even the active regions that are not productive at all? Well, we know that, as I said, we don't have a lot of active regions to really study systematically and address this, perhaps for every active region, because we just observe them. Only a small fraction of the active regions over the solar cycle are observed to appear on the to emerge, from our vantage point. So we have a reduced and limited data set to work on that. However, irrespective of whether we capture the onset of emergence or the birth of an active region, emergence may happen at later times as well, and we typically call these active regions emerging active regions, nevertheless. And we know that they are most flare productive than decaying active regions. For example, Shriver 2009 has discussed that. And of course, I addressed the increasing complexity. And when we talked about the delta spots, we know, these are just the top candidates for explosive and potent and disruptive activity that can potentially cause lots of problems in the geospace. Many models have been proposed. Here I have just a list. You can perhaps put more publications in that list. I just show a few representative publications. People have discussed how active regions get energized as they evolve, either through sunspot rotation, see sunspot rotating, either through MHD instabilities, which basically do not really consider how you come to an unstable structure, but how the structure becomes triggers an eruptive flare. Shearing is a process that has been proposed. For example, the breakout model is based on this. Tether cutting is another process that is well referenced, which also involves shearing. It doesn't involve cancellation, for example. Magnetic cancellation has been discussed, for example, in decaying active regions, and emergence in general as a term. Like, we have an emerging active region, therefore it should produce explosive activity, right? Like, the bodily emergence of a magnetic structure, or the sort of reconfiguration of the emerging structure later on, through torsion alpha waves. I think Yuhong has made some work on this. Bodily emergence, as I said earlier, which is a strong term, because we don't really have bodily emergence in a strongly stratified medium like the convection zone is, especially at the top layers. So you have the pancaking of the magnetic flux, but nevertheless, this is out there as an idea, assuming that you have already made flux ropes that are emerging, and then, boom, you have an explosion right after. I think you can see just by the number of the different models that we have inconclusive evidence. It's just too many opinions out there. So it may that all of them happen at the same time, or partially, or maybe some of them are just an illusion. I'm not calling an illusion the work of a lifetime of people. I'm just saying that it might be that we are attributing some mechanisms more importance than some other mechanisms. So that's a possibility. And in order to address that, we really need to do a thorough comparison, perhaps through modeling. Nevertheless, conclusive evidence. But one thing you will notice from this list is that something is missing. And that thing is missing is what I think is something that could have been addressed before. But it may be that is omitted because it's very difficult to characterize. And that is magnetic cancellation during emergence. What do I mean by that? You'll see soon in the following slides. It's this model that we propose. It's the collisional shearing scenario. Basically, you have two. If you focus on the top left figure here, we have one bipole here and one P1. And another bipole here and two P2. And the white arrows, if you can see them, they denote proper motions. So they're just emerging and naturally separating from each other. but they're positioned in a way, as you saw in one of the cases that I showed you, that eventually collide. And when they collide, they're producing the so-called collisional polarity inversion line. So it's still a part of the internal neutral line of the active region, but we call it collisional just to denote that this has developed as a result of a very strong proximity between two sunspots. When I say strong proximity, essentially, you can really see the sunspots deforming, collision. So as this happens, and as emergence really is driving the proper motions of these polarities, what happens is that the shear, as one polarity is moving that way and the other one is moving that way, is driven by that process as well. And the cancellation at the same time is driven by that process. And we want to call this process separately from cancellation. We call it collisional shearing because we want to show that it's a bit different as a concept than the classical or the canonical cancellation of Balegoihin and Martens 1989, which considers cancellation within the internal neutral line of a conjugate dipole, essentially a simple bipolar structure. And that's really the numerical model, right? So we propose that, and at the same time, we propose that this process develops actually because it's during the emergence, we naturally have faster proper motions and faster evolution. The canonical cancellation scenario is actually based its evolution into the supergranular diffusion, basically the natural decay of magnetic flux as polarities disperse, and also differential rotation for the shear. Here we actually say this is actually happening much faster because the shear is driven by the emergence of the individual bipolar elements, bipoles, bipolar magnetic regions, and therefore is much stronger, and it can be energized in active region much faster than an active region is energized at the later phase because of these effects. And then we ask the question: is this all of this framework or all this theory here able to explain the formation of energized structures, essential magnetic flux ropes, and therefore their explosive activity later on? So that's really the big question. In our previous publication in 2019, we tried to address this question by performing measurements. So all of that is good. Yeah, you have two polarities close to each other. How do you know they cancel, right? Well, we actually quantified the cancelled flux in these two cases that are very easy to deal with. Of course, if you have very, very complicated cases, it's even harder to do it. But we performed the measurements. You can read it in the paper. I don't have the time to go through the details. We introduced a method called the flux deficit method, where just quickly, we use the polarity that if this is one conjugate dipole that we know because we can track the evolution of an active region, and this is another conjugate dipole here, we can actually take the flux of this polarity that is not colliding with any other polarity as a reference point and track the flux of the polarity that's colliding with another polarity and actually measure the deficit. So the theory is that says that if there is cancellation, you should see a deficit. If there is no cancellation, you should see a balance, you know, within the instrumental accuracy and other secondary or tertiary effects that get into flux balance in actual magnetograms, right? You may have contamination here. So anyway, it requires very clearly and very well isolated cases to convince yourself. And we actually propose that these two cases are actually having the essence that we need to use as test cases to propose to actually convincingly show that cancellation happens. It's in such active regions during their emergence phase. And indeed, we found significant amount of cancelled flux of order 1 to 2, 10 to the power of 21 Maxwell. So for those of you that are into studies of active regions, you know that this is a significant amount of flux of an active region. So the reason we do not see it when we make flux plots is obviously because emergence is dominating, overpowering this effect, right? If you had cancellation, you would be having emergence if it was stronger than emergence, right? So that's why this has not been seen before. And that's why this is not seen unless you actually do this kind of differential measurement that I call it. So basically, you have to do that carefully. Same thing for a more complicated case. So I invite you to look at the paper and actually look at this particular methodology. And then we ask the question, because, okay, we have cancelled flux. Does that cancelled flux amount to the poloidal flux in the corona, essentially the flux of the flux rope itself? To address this observationally, first of all, we look at the evolution in the atmosphere, the solar atmosphere, and we're using AIA data for that. And in the paper, we discuss these two active regions, as I said, and here uses just two snapshots. And we also have movies, of course, and you see the brightenings along the neutral line, the collisional component of the neutral line that eventually develops a flux rope candidate structure, a structure that as we observe it in the solar atmosphere, it appears to have the manifestation of a flux rope, a sigmoidal-like shape, hot channel. When we say hot channel, meaning to actually appear in hot in wavelengths that are actually sensitive to hot plasma. And that's really what you see. You see 131 is the green-colored layer on top of these magnetograms here. Same thing for the other active region. So yeah, I invite you to actually even look at the movies. And you're going to say that was okay. Two active regions. You didn't belong to two active regions. Okay, what's next? Well, some other people have picked up on this idea, and they have done a statistical study investigating the idea of collisional shearing, and they have found collisional shearing to happen in almost 90% of the cases that they studied. In this case, they had a sample of 19 active regions. So, yeah, it appears that more work needs to be done, but at the same time, it seems that it's more and more plausible that this is a mechanism that may contribute to the energization of an active region. Now, one would ask, okay, we see cancellation. I mean, where does cancellation happen? And we only observe the photosphere. Is it that this is an aftermath of reconnection events higher from the photosphere, or is it something that happens below the photosphere? And essentially, even though we see cancellation, it's really emergence of a U-loop structure, which will still give you the same manifestation of flux cancellation. And to do this properly, you see here a very nice figure. I kind of adapted it a little bit just to illustrate with colors what I want to show. When you have cancellation or reconnection below the surface, below the photospheric surface that the magnetic sensitive line we're using for HMI can observe, we cannot really see below, you will see a blue shift above the neutral line, because you will have the upper end of the reconnection outflow, essentially. And you will have a retraction that goes back into the solar interior, and all of that will happen just below. So you're not going to see anything. You're just going to see emergence and cancellation at the same time. Well, U-loop emergence, you're going to see Doppler shifts, blue shifts, but at the same time, annihilation of magnetic features. And keep in mind, this was proposed for quiet sun features, the kind of movie I showed you in the beginning, with the supergranule and the salt and pepper structures and the multiple bipoles all over, canceling, emerging and canceling all the time. So all I'm saying, I try to have you think that this may happen in an ordered fashion along the neutral line, to give it some guide field or whatnot, because it's just a 2D representation, right? And the opposite scenario is when you have a reconnection happening just above the surface. And according to the Van Palehoiken and Martens scenario, which is here, that's what they consider. They consider this mode from Swan et al. Swan 1987. So you have cancellation just above the surface, or maybe just to the lower end of the chromosphere, and then you have the submergence of an omega-shaped loop, which will still give you the manifestation of cancellation, but you will get redshift in the neutral line, essentially. So we did this kind of exercise in the same application, and we did find preferential evidence, preferential redshifts over blue shifts in the neutral line, or the area of the neutral line. Now, keep in mind, HMI, okay, yeah, it has 0.5 arcsecond pixels, and it's not a true spectropolarimeter, so you may take these results, with a little skepticism, which is completely fine. I will share your view. But the update I should give is that we have verified these results for both of these active regions that you see on your screen with Hinode spectropolarimetric data. And we are preparing the publication, and we actually verify and confirm the results, which is actually a very big surprise. We were expecting to see noise, for example, but turns out it's a very robust finding. So what is left now to beyond the observational discussion of evidence for collision shearing and the phenomenological model that I discussed earlier, we want to test this out and essentially see if we can make an actual numerical model of collision shearing. That's what you see here. What we did, we took one case of collision shearing. By the way, collision shearing can happen both when you have two flux tubes emerging simultaneously and also when they emerge sequentially. That's probably doesn't even need to be stated. So we take this case where you have two flux tubes emerging at the same time, side by side, and as they emerge, they will develop a neutral line because of collision. And we model this with two flux tubes using some analytical functions for a torus. And we have another torus here that we actually shifted properly so that we can emulate the phenomenology we see on the surface when we have two collisions. And I think now some of you may actually already understand what is the inspiration behind this particular setup. So this is a movie, actually. It shows the two bipoles emerging and then colliding. And when they merge, they have their own self-polarity inversion lines. And where they actually collide at some point, they form a collisional polarity inversion line. So that's actually one of the two active regions I showed you earlier in movies from real active regions. But we model it in this kind of idealized way. So as we have this kind of structure, we assume it emerges with a constant speed of 1 kilometer per second. And we can also extract the electric field at the photosphere, and we can use it to drive a data-driven magnetofrictional code, in particular the one developed by Chung and De Rosa in 2012. And get ready to see the results. This is the movie. And what you see in this movie is actually a volumetric representation of the fractional twist number. So what you see is the voxels, or the particular grid points in the simulation that are perforated by magnetic field lines of a certain twist. Every field line has a certain twist number, right? To be correct, it has to be considered with respect to an actual axis in order to do this kind of measurement correctly. But there is an analytical theory, and there is a measure which is called the twist number, where you can calculate this kind of quantity on a grid point by grid point basis, and you can make a movie of that. So basically, anywhere you see those volumetric colored pixels, and here is a scale. This is the twist, so it's cropped here. I filter out any field line that is actually below one full turn. One full turn, some people consider it as the minimum threshold to consider magnetic field lines as magnetic field lines with flux rope. So what you see here is mostly yellow colored, so you're above 1.2 or so, 1.3 turns, which is well within the domain of values for the twist number that you would consider as a flux rope. And the other thing that you see actually recurrent formation of flux ropes in this collision and neutral line. And that's really a major result. The other thing is when you really find such twisted magnetic field lines in your model, you want to understand the stability, and the way to do that is to actually calculate the so-called critical height and see if things are consistent. Critical height is basically the height where if a structure expands, if it reaches it, it will become unstable. That comes from the torus instability theory. And it's essentially a result of a magnetic field that is having a strapping effect on a twisted magnetic field structure that is forming just above the neutral line. So anything that is overlying that magnetic field is essentially a magnetic field that is having a downward tension force, and it pushes it, introduces a Lorentz force that pushes it downward. And this is a movie that shows how the critical decay index height really evolves. And it appears that here you see two cross sections. One is along the X direction, one is along the Y direction, where these two dashed lines are. So this is the Y slice, which is this horizontal component here. And you see the twist number now colored as grayscale contours. and the decay index height shown with those magenta contours. And you can see the growth of the flux rope just here. I know the movie goes really fast, maybe I can just slow it down a little bit. So you can see this is the flux rope that is forming along the neutral line. You can see that is actually reaching this particular critical height. We don't care that there is a critical height that's closing as a bubble. This is still well understood in the theory. You only care about the one that is actually the first one you reach, and that's really what defines evolution. Then you have that again. You have another flux rope forming, and the same thing goes here. Oh, you can see that here in the vertical cross section of the flux rope. Maybe that's a better representation here. When this happens, whoop, eruptive. Whoop, again eruptive. So that's really the major result. We actually have 4 different eruptions in our model within this evolution. And what you see in this movie at the bottom is essentially axial and poloidal cuts. So basically we define an axial cut as a warped surface that is following the curvature of the collisional polarity version line. So what you see here is really that. And the collision polarity version line obviously changes size as it evolves, so that's why you see these panels to change size. But the axial cut, we keep it fixed because it's always perpendicular to the polarity version line. You can still see different quantities here. You see the twist number, you see the logarithmic squashing factor, which shows essentially the topology. You have a quadrupolar topology, and therefore you have 2 intersecting quasi-separatrix layers, and the flux rope is forming just underneath that. And the critical thing to say here is that this is a recurrent reformation and eruption of flux ropes. And this is happening because we are actually allowing for flux to cancel at the bottom boundary. So basically, you're continually canceling flux. Once the flux rope is ejected, this cancellation still is ongoing because it depends on how the positive and negative polarity are positioned and how much flux is canceling between them. And as you see, this is canceling, for as long as they have actually close contact. And the summary plot of what you saw in terms of movies is actually here. That may require a bit of an explanation, but it's not really that difficult. If you focus on the orange line, this actually shows the constant flux in the simulation, which is something we control. We control the way the positive and negative polarity are moving against each other, how much they're canceling the flux via superposition, by the way. I neglected to mention that. That's how we define our boundaries. That's a simplistic model. You'll see another model in the following slide that is actually more realistic, and therefore we have a nice number for that, and it's really our reference number. And then the big question is whether the flux rope that is being formed is formed as a result of this cancelled flux. And what you see with different colored curves here is really a measure of the flux rope flux, which is really the poloidal flux in your system. And what you see is that with the vertical lines is the onset of the eruptions. I'll explain what is the plot down here. And you see that the growth of the poloidal flux above the neutral line essentially follows the trend and reaches the point of the actual cancelled flux, and then you have an eruption. Once you have an eruption, we don't track this flux rope anymore. It's a CME. It's gone, right? And then we actually start seeing the formation of another flux rope. And we start measuring the flux right after that, right here. And look at that. The second eruption was also having a poloidal flux that was consistent with a cancelled flux. The third eruption, similarly. The fourth eruption is a little bit different. You see the cancelled flux is actually reducing. The reason is we purposely set the superposition of the 2 polarities to actually go a little offset after a point to explore the so-called effect that we discussed in our 2018 paper as re-emergence. When you have 2 polarities colliding, you have cancellation, it's fair to assume that once they go past each other, maybe they will make space for flux to re-emerge. And that's why we did that. And indeed, at that point, the other eruption is perhaps happening because of this re-emergence. So there is a little bit of cancellation still, as you see after this third eruption. So you have a seed flux that is actually contributing to the poloidal flux, but then after that, it's just an emergence that is pushing this flux rope, and then it's standard model reconnection, forming your poloidal structure quasi-statically, essentially kind of like tether cutting reconnection, and then you have the eruption. And here you see exactly the same plot, only that you imagine that we drill a hole, or we extract, the way we extract slabs or columns of ice from the Antarctica. We extract a column of pixels of the volumetric twist number in the simulation just above the core of the neutral line, and we make a stack plot. Basically, it's a space-time plot. So you basically see if you have an eruption, that the twist number is going higher places, and higher heights. And this is very consistent. Here you see the time between the different eruptions. So we have an eruption about 2.2 hours after emergence. Then there's another eruption 3.6 hours after the last one. And there is another one, again from the reference point. Now there is another one 5 hours, almost 7.6. This looks very consistent with a succession of eruptive events in extremely flare productive active regions that exhibit exactly the same characteristic evolution. So that's really the takeaway message for that. And I think I'm nearing the end of my talk. I just want to show you the future outlook here, and I promise to show you a more realistic simulation that was done by Matthias, and we are part of a team, Matthias, myself, and Mark Chung. And we are preparing a publication right now that will feature exactly this result. And what you see essentially is a 3D radiative MHD model of collisional shearing. Let me play the movie, and maybe I'll let it speak for itself. But nevertheless, what you see here, you see a simulation that contains a shallow layer of the convection zone. You have two sunspots that are actually advected from the bottom boundary through the upper layers of the convective zone, which makes the sunspots essentially to translate and also assume other hydro or MHD effects as they're moving. And then you're forming collision and polarity version line. And then you have the synthesis of AIA-like observables, for example, 304 data looking top-down or from one side or the other side, and 171 and 94 angstrom data. So now get ready for the eruption. So there was a formation of a flux rope. There was a successful production of a CME as a result of collisional shearing. How do we know it's collisional shearing? It's because we actually see cancellation. If I had blown up this magnetogram, you would even see it by eye, that there is indeed a reduction of flux. So more work needs to be done, of course. That's a major result, that we replicate the simplistic models results, or we replicate what we think the sun is doing. I mean, at least comparing the phenomenology we see in the synthetic data with some well-observed active regions. But the next step, obviously, will be to utilize decreased observations to study the collisional shearing physics, which will require multi-height magnetograms, to track how the magnetic fields are really reconfigured, or if where is the reconnection height, for example, from the surface of the sun, and also this investigation is very, very relevant to the MUSE MIDEX. As you know, MUSE has been selected earlier this year, and it will be a transformative mission. It will actually allow us to probe the sun in higher resolution than AIA does, but at the same time be able to see Doppler maps, and at the same time being able to see thermal width or width maps. So we can actually get to look at the thermodynamics of active regions and how these are changing, and also the precursor activity in active regions, and do this kind of study. You remember the list of different models I showed you in one of my slides. So sunspot rotation, shear, cancellation, you name it. We can actually do all those kind of tests, hypothesis tests, and see what is really the major process that governs eruptive activity on the sun. At least in recurrent eruptive activity. You may have eruptions in small features like jets, but we're talking about here what happens in large-scale active regions, and in this kind of scales, this kind of fluxes, this kind of energies, free energies and energies, and this kind of impact or potential impact for our advanced technological civilization. So that's really our focus. And just quickly, it will be very nice. I complained earlier in the beginning of my talk that we do not really observe the entire sun 360 without waiting too long for a true 360 surveillance of the sun, with perhaps with a constellation of satellites. It may be possible to do some sort of work using solar orbiter phi data And that will help us to get better constraining our boundaries, the boundary conditions, basically, because we want to do it for actual active regions, so it's not going to be, we know that there's systematic effects and errors, and perhaps this can be alleviated by, some of them can be alleviated by having multiple viewpoints, for example, combining Solar Orbiter with HMI and correcting, for example, for the 180-degree ambiguity. That's one possibility, and see what we get from the models. That may help make progress in that direction in understanding the recurrent flaring activity on the sun. The other thing that I think is important to also characterize is determining the total amount of activity in active regions during their lifetimes. So as Solar Orbiter will co-rotate around the sun, or quasi-co-rotate, really. We are also limited by how much time Solar Orbiter will be taking data. So as you know, it's only a fraction of a year. So it's only a few months at best, or 1 month or so. And of course, they will run other modes as well, other observing modes. So ideally, we will have had a long period of observing an active region from its birth all the way to its decay. That would be really great. And even better if we do it from multiple active regions, determine the total amount of currents and flux during their lifetime of active regions. That's also perhaps important. We have some evidence, of course, from studies over the previous decades, but just by looking at the sun from our vantage point. But that's definitely not a complete study. None of them are complete studies in the sense that they do not really track the actual lifetime of active regions. So that will be really important. Now, I'll skip that about the electric field. We don't have much time, I think. And in general, we want to understand the process of filament channel formation. That's really what it's all about. You have filament channels forming in the quiet, well, in decaying regions or polar crown regions, but you also have filament channels forming in active regions. And yeah, the physics, as I mentioned earlier, or the dynamics may be different, but we want to actually see what is the detail. What are the detailed physics about forming filament channels that eventually become eruptive? So a synergy of multiple observatories, including DKIST, is important in this case. And yeah, that's kind of a long summary, but I think we covered quite a lot of things. And I can take questions now if there are any.
Thank you very much, Jurgis. And are there questions? We have time for maybe 1 or 2 quick questions. Okay, I'm keeping an eye on the chat, on the raised hands and so on. But in the meantime, I have my own question. Well, actually, several questions. Okay. So it's an interesting work about replicating the active region that just kind of continues flaring. Just a few questions to clarify. So one question is, if you merge the flux ropes separately, I mean, without colliding them, are they stable in this particular simulational setup?
First of all, we do not immerse a flux rope. Maybe I did not explain properly. Maybe for brevity, I omitted to say that the 2 flux tubes that we are emerging are non-twisted. There is 0 twist in the flux tubes.
Okay, that would have been my second question, actually. So thank you for asking.
Right, of course.
Are there questions? Sarah?
Yeah, following up on that, I was wondering with because I know that Yu-Hong did some stuff with some recurring eruptions with PLA Chatterjee a while ago, and one of the things there was that you had the flux rope that formed, but when it erupted, it basically was reconnecting internally, and there was some of it left behind. Do you happen to know in those flux ropes erupting, is it a complete or a total eruption or a partial eruption of those flux ropes?
That's a very good question. From what we see, I can probably show you the slides, it appears to be a complete, at least in the simple model, a complete eruption. You see that the twist number is completely depleted. This is actually time and this is height. And imagine we are actually taking, we're extracting a column of pixels just at the core of the neutral line at all times, which is where the flux rope is forming. So this is the formation of the first flux rope, and then actually becomes unstable and ejects. And then you have basically a depletion of twist here, which suggests you don't have a flux rope there anymore. And you have a second flux rope forming slowly. And then, boom, Same thing for the other one. Same thing at least that's what we see in the idealized model. In the MHD model, we still have cancellation going on, which means that we still see the eruption. I don't have the time to show you data. I didn't prepare actually, so the analysis of that. But please stay tuned. That will be an upcoming paper. But we do see some leftover twist around the area. However, what is not what is a certain thing to say is that most of the flux is actually ejected as a CME in this case. So both of them are behaving in such a way that most of the flux is actually ejected and not partial per se.
Yeah, just a quick comment that it sounds like that does sound like what's happening. One thing Yuhong and I would do when we were looking for this was we were looking for the bald patch and the separator surface as an indicator of the remainder of some of the flux rope. And so I imagine you've got that in your QSLs as well, right?
Here you see the movie of the QSL. This is an axial cut. So imagine a cut that's perpendicular to the neutral line.
Yeah.
And if I pause it, that goes really fast, but you can actually see a new flux rope forming just underneath.
Yeah. So it's gone. Yeah.
Yeah.
Okay.
Completely gone. Yeah. Yeah. Mm-hmm.
Oh, another follow-up question, just what happens to the energy?
The energy is increasing, and that's go on. Sorry. Mm-hmm.
Oh no, go on.
The energy is definitely increasing as for with more emerging flux, right? So I think this is really something that is not surprising, and I would also argue that just by looking at the energy, we cannot really tell much about whether we're getting closer to an eruption or not. So it is consistent physically, but I think looking at the global quantities like energy and helicity, it's really difficult to make any predictive assessments for what happens. Which is why I think with those simulations, the point we want to make is to look at the local physics and not at the global physics. The global physics, you have a monotonic increase, more or less, right? Yeah, you may have some drops after a CME, for example. But that's not what we're considering here. We're considering the fact that we have an active region that we study or we model from its very birth all the way to the phase that is actually not eruptive anymore. And you definitely see a monotonic increase, both in terms of helicity and energy, as a zero order.
You totally okay. If I were the referee of a paper, I would totally want to see the plot of helicity, a plot of energy, and a plot of free energy in such a paper for sure, because it's interesting.
Of course. But what I'm saying,
Very
yeah,
good point.
absolutely. I'm saying there is nothing new. There is nothing new there with respect to previous studies. That's what I'm trying to say. So it's consistent, the energy and the helicity. But we argue that this is probably the reason why we haven't really made a lot of progress. If we look just at the energy and the helicity, that's all you can say about active regions. You know that an emerging active region will increase in energy. And if it has the conditions to actually increase its helicity, for example, either through, with any of those mechanisms, sunspot rotation or anything, right? You will still see an increase in helicity. But then when is the moment of the onset of the eruption? The way to tell is actually when you can model active regions and when you look at the particularities of that. And I think cancellation, which is what we demonstrate here during the emergence phase of active regions, is really, it's a very strong candidate for explaining recurrent explosive activity. Not just emergence itself, but cancellation. That's the main point that I'm trying to make. Yeah.
That is really interesting. Thank you. Are there more questions for Yorgos? Samaya?
Yeah, just a quick question. So it seems like, if magnetic reconnection is happening as these two flux are colliding as they're emerging, it will be a larger response from the chromosphere and the photosphere. I was wondering if you had some way of understanding how much energy is deposited during that process, and what kind of response would you expect? I know you talked about blue shifted and red shifted flows, but it seems like it would be a much greater signature if you've thought about that.
That's an excellent question, and different models. Actually, let me just say that the previous models, for example, breakout or tether cutting, they traditionally are the breakout is actually, an MHD model, but they do not make predictions about the manifestation of what we'll see in the chromosphere, for example. They do not really include the physics for that. Same thing for tether cutting. One would need to do accurate modeling of those different use them as essentially configurations, and then include accurate radiative convective physics, as we do with MURAM, for example, to produce synthetic observables and then address the issue you just brought up right now. What is the response of the chromosphere, for example? But this is a very, very different and difficult topic, in that if for the chromosphere, it depends what line you're going to use. You may need to do non-LTE modeling, and those are very, very computationally expensive models. But that's a very, very valid point. And the way to utilize observations, for example, from DKIST and even from IRIS that we have over the previous decade or so, in particular for IRIS, one needs to use advanced modeling. We cannot just solve problems in solar physics with cartoon models. We really need to use advanced modeling. And I agree, the more inclusive the models are, or similarly, the more wavelengths we use when we want to study an event or a particular phenomenon, the closer we get to its physics, and the closer we get into understanding fully what's going on. So yeah, so that's an ongoing work. As you see here, we are synthesizing some observables. Those are coronal. Well, 304 is not exactly coronal, but anyway, transitional region-like. Yeah, it will be very interesting to see how the chromosphere behaves during this process of reconnection. If reconnection is happening above the surface, for example, it's not that you may expect to see just the blue shifts or red shifts. You may also expect to see changes in the line width, or maybe changes in the intensity. If it, for example, if it happens in the chromosphere, you may be able to see transient brightenings there that you don't necessarily see in the corona, for example. So all of that happens there. That's an excellent question, and I think it merits a different presentation.
Yeah. Okay. Cool. Thanks.
Yeah.
Cool work, though.
Well, we are getting past the hour, so if you need to leave, please leave. But also, if you have more questions for Yorgos, now is the time. Okay. May I ask a quick question of my own? It's kind of selfish. It's kind of a selfish question. But I've been hunting. I'm on a project in which I'm hunting for the dipolar active regions, and it had been more than once that I've been pondering on whether particular structure is dipolar or not. And I was wondering if the literature has any formal definitions of such.
If you go back in time, like decades ago, the resolution that they had with those instruments that they had and the time coverage that they had, that's what they used to define a dipole, right? What they thought as a dipole, if they had, sporadic magnetograms, it may have been a simple dipole, but nowadays with continuous surveillance, you actually see multiple features emerging, even for a simple dipole. So it is definitely true that it's not a unique definition in terms of what makes a single dipole, but there are definitely some active regions that are more textbook-like when one considers a dipole. Say it again?
That is very true. Yeah.
Yeah. So, but they're not that many. Most of them are actually complex, and they disperse, with different rates, and they may have sporadic emergence activity. So overall, at the end of the lifetime of an active region, give it some time, it will still look like a dipole, but it will be a decaying dipole. So it really depends what you want to do. If you're looking for emerging dipoles, you may be able to find a nice case, perhaps up to a certain point until another emergence event happens, or so it will be reduced in terms of lifetime, right, or time you have to consider, or you can still be happy if you just use a decaying active region as a dipole, because that's good enough for the modeling you want to do. So it's kind of a difficult question, but we have to accept that there's inherent complexity on the sun, and it's kind of a qualitative description at some point what composes a single dipole. So
thank you. There is a raised hand by Samaya.
Sorry, yes, one more question. I thought it was really neat that the model predicted these eruption time scales for the homologous eruptions. So because that means you get kind of also a time scale for flux rope formation. And I was wondering, of course, because
Exactly.
I like jets. Have you thought about if this scales to other for smaller flux ropes? And if if you compared that time scales to flux rope, what you see in data, from eruptions that
Right.
you see in real data, bigger, larger ones, and how long they take to form versus smaller ones, and how long it takes to form, and this kind of thing.
We haven't. That's an excellent topic for a statistical study. There are definitely lots of studies in the quiet sun because this is really easy to find. Now people are talking about mini filaments and whatnot, and talking about jets. But then you have to also consider not just the size of the neutral line, which is I think what you basically ask when you're talking about scales. You also have to consider the time scales. When you go to more decaying active region-like conditions, the neutral line might be sometimes even bigger than the original active region because of how the field is dispersing. So you're going to have a huge neutral line, but then the evolution of how you build a flux rope because of cancellation in this particular case, you cannot really apply anything else to that, I think. It will take time to form it. So the time scales will be, perhaps of order of days, if not a day of order of days, not of order of a few hours, as we see in emerging active regions. For small scales, though, if you go now quiet sun, but small scales, like the mini filament eruptions and jets, you have small neutral lines, and you have the buffeting. So if I go to, I should do it, but maybe I can do it to show you this plot here. This movie, you see scales of all kinds, right? You see cancellation happening everywhere. It's possible you see mini filament eruptions everywhere, but whether this is going to be a very fair comparison with respect to active region size flux ropes, it's a different story because here you have different driving. Essentially, you have the photospheric motions that, for those kind of scales, perhaps matter in that way than if you go to larger active region size scales. Those kind of solid pepper photospheric motions perhaps mean nothing. They do not really do anything. So it's a matter of how monolithic your neutral line is. It's a matter of how consistent your physics are in those two colliding polarities, so to speak, if this is what we're getting at. And you're going to get a spectrum of these when you go to small scales. But there are already studies, I think, about that. All I'm saying is that for large active regions, it's really hard to generalize. We don't really get exactly the same scales, not in terms of time, not in, of course, in terms of length scales. So yeah, I think we have to study those beasts, with a proper framework, I guess, or I don't know, like understanding that small scales and quiet sun develop in their own time scales and may even be depends what you really look for. If maybe even if you want interested in waves, these things evolve in terms of seconds, right? But anyway, I think it's better to look at the literature and see what has been done, and perhaps there is something there based on what you ask.
Thanks.
Well, thank you again, and Jorgos, thank you very much for the seminar, and
thank you for the invitation.
And yeah.